In this video, I'm going to go over your Unit 5 review, going over the integral. So first up, I have some indefinite integrals. So indefinite integrals, we're doing the antiderivative. So you're thinking what you would take the derivative of. That would give us this result. So undoing this one will give me x to the fourth. This will be minus x cubed plus x squared minus 4x, and we always want to remember our plus c. The second one, you could do it without a u substitution, but I find it eliminates some of the errors that we might see. Okay, so I'm going to replace my du with a 3dx. I don't have a 3dx though, so I'm going to sneak a 3 in here, but then undo it on the outside. Okay, the 3dx becomes my du, and then my 3x becomes u. So we have sine u du. Derivative of cosine is a negative sign, so when I do the integral of sine, we get a negative cosine. And then with these indefinite integrals, we want to substitute back in our u. I'm going to do a u substitution again here. This one's a definite integral though. So we're going to let u equal tangent. When I do a definite integral with u substitution, I can just change the bounds. So if I plug in pi over 4, tangent of pi over 4 is 1. Tangent of 0 is 0. And my du is secant squared, which is right there in our problem. So my new limits of integration are 0 and 1. Instead of tangent to the 8th, tangent's now going to be u to the 8th. And then secant squared dx becomes my du. So then we get 1/9 u to the 9. Evaluated from 0 to 1. We do not need to substitute back in because we changed those limits of integration. End up getting 1/9 out of that. Okay, and this next one, you're told what to do for your u. So u is x over 4. Okay, which will get replaced here. We are going to go ahead and change our limits of integration because all of these answers are in u, which means we need to substitute. So 4 divided by 4 is 1, 0 divided by 4 is 0. From that alone, I can eliminate the ones that don't have those limits of integration. My du is going to be 1/4 dx. Okay, so I'm going to put a 1/4 there and then undo it with a 4. So I'm going to have 4 times the integral. The 1/4 dx becomes du. And then I get radical 4 minus u squared. So this is going to match option B. Okay, these two, cosine over sine and sine over cosine. Of course, this is cotangent, and this would be tangent. But in order to evaluate these, we'll do a u substitution. So I'm going to let u equals sine of theta, whatever that denominator is. So du is going to be cosine theta d theta. Okay, so cosine theta d theta becomes du, sine becomes u. The integral of 1 over u is natural log. And then we'll substitute back in because this was an indefinite integral. We'll do similar here. I'm going to let u equal that denominator, which is cosine now. My du is a negative sine theta d theta. So I need a negative, so we'll have a negative here too. So we get negative natural log u, absolute value of u, and then we'll substitute back in. Okay. Oftentimes it's on us to do some algebraic manipulation in order to be able to do the integral. What we can't do is just do the integral of this times the integral of that. It just does not work that way, just like it doesn't with derivatives. So this is the same as x to the 2/3. Okay, so what I can do is distribute that through. If I'm multiplying x to the 2/3 times x to the 2, we're going to add those exponents together. So 2 would be the same as 6/3 plus 2/3 is going to give me an x to the 8/3. Adding 1, which would be 3/3 to 2/3, would be a 5/3. And then if I multiply the 3, we get 3x to the 2/3. Okay, now, when I do this, we're going to add 1 to the power. So if I add 1 to 8/3, I get 11/3. And then we divide by that or multiply by the reciprocal. Because if I did the power rule and multiplied 11/3 times 3/11ths, it would go away, which is what we're looking for. Here I've got the 2, I'm going to leave a space. I'm going to add 1 to this power, so that's going to be 8/3. And then we're going to multiply by 3/8. Add 1, I'm going to leave a space. Add 1 to 2/3, which is going to be 5/3. And then multiply by 3/5. So if I clean this up, we get 3/11ths. X to the 11/3 plus a 3/4 x to the 8/3 plus 9/5 x to the 5/3 plus c. Okay. Next we're going to find the Riemann sum in the limit statement that's going to equate to our integral symbol here. So we've got the integral from 3 to 5 of x to the 4th dx. So what we're doing here is I've got some function, x to the 4th, I'll put a generic thing here, and we're integrating from 3 to 5, where these represent different rectangles. Okay. Well, if this is 3, I'm taking the distance from 3 to 5 and I'm cutting that into n rectangles. So the width of each rectangle is going to be 2 over n. However many n we want to squeeze in there, obviously we want n to go to infinity. So each of these widths is going to be 2 over n. Okay. The height is going to be the function value, which is x to the 4th, evaluated at whatever endpoint. Well, if this is 3 and this distance is 2n, then the function value we're going to be plugging in is 3 plus 2n. The next one would be 3 plus 4 over n, because we would have added 2 over n and 2 over n. So the widths of all of our rectangles are 2 over n. Our heights are going to be 3 plus some amount of 2n's that we're going to add to that. So going back to here, my widths are 2 over n. So there's my width of 2 over n, not 1 over n. And we're adding 2n k times to our 3, not just k over n. Next we have one of the parts of the fundamental theorem that I'm taking the derivative of an integral. So what we're doing is we do the antiderivative and then we turn around and do the derivative. So as a result, whatever our variable is here gets replaced with the x, and that's it, because if we integrate with the constant and then took the derivative, constant goes away, so we're just left here. Now, if instead of just an x we have a function, we sort of handle it in the same way. But instead of x going in place of t, we're going to have cosine of x in place of the t. And then we're going to multiply that by the derivative of cosine, which is a negative sign. So we have to do the chain rule when we're doing the derivative. If we have two functions, we're going to have tangent squared the top, x cubed, instead of the t, times the derivative of x cubed, which is 3x squared, minus tangent squared the bottom one times the derivative of x squared, which is 2x. In our next one here, we want the limit as h goes to 0. Well, if I plug a 0 in here for h, I mean, the integral from 1 to 1 of, I don't care. If it's 1 to 1, it's going to be 0. And then in the bottom, if I plug in a 0, we get 0. So 0 over 0 means we're going to be using L'Hopital's rule, which means we can take the derivative of the top and the derivative of the bottom. Well, just like before, the derivative of an integral, those are opposite operations, so they cancel. So I'm just going to be left with the square root, but instead of the x, we're going to replace that with 1 plus h cubed plus 8 times the derivative of 1 plus h, which would just be 1. And then the derivative of h is going to be 1. So now I can plug in 0. Okay, 1 cubed is 1, so we get the square root of 9, which is 3. Next, I have a bunch of different integrals, and we have to decide what strategy to use. And we have a lot to use. Use substitution, all of our known antiderivatives, but sometimes just good old-fashioned algebra. So here, these two are very similar. The difference between the two is this one has an x cubed, which is going to allow me to do a u substitution. Here, I don't have that. So I need to FOIL this out. Okay, so in my FOIL process, we'd be multiplying x to the 4th times x to the 4th, which is x to the 8th. My two middle terms would be a 3x to the 4th, so I have 6x to the 4th. And if you need to do this in a couple steps, that's fine. And then 3 times 3 is 9. Now I have something I can integrate. So this will be 1/9 x to the 9 plus 6/5 x to the 5th plus 9x plus c. Like I said before, though, this one I can use a u substitution. Now, that being said, you can FOIL this out, then distribute, then integrate, but a u substitution can make our lives easy. Okay, so we use a u substitution when we have a function inside another function, and its derivative is at least removed by a constant there in the problem as well. So we have 4x cubed, which we sort of have. So I'll sneak a 4 in with that x cubed, but I don't want to change the problem. Okay, the 4x cubed dx becomes du, and then the x to the 4th plus 3 squared is now u squared. So 1/4 times 1/3 u cubed. And then replacing back in our x, we get 1/12 x to the 4th plus 3 cubed plus c. Okay, so looking at these next three, they all look very, very similar. There's little changes. This one I can do a u substitution. Well, my 6x would be the same as 3 times 2x. So when I do the replacement, instead of a 6x dx, we're going to have a 3 du, because if I multiply 2x times 3, we get 6x. And then my whole bottom becomes u. So this will be 3 natural log u. And we get 3 natural log x squared plus 1 plus c. Here I can do the same u substitution. So again, I'm going to let u equal x squared plus 1. Du is still 2x. So I'm going to get a 3 du over u squared. This is not natural log. So the derivative of 1 over x is negative 1 over x squared. So this antiderivative is going to be negative 3 over u. Now, if you don't recognize that, just turn this u into a -2 power, and then just do the power rule, and you'll get the same thing. This one, unlike the previous two, a u substitution isn't going to get me anywhere because we've got an x squared instead of just an x. In this case, what we're going to use, because the degree is the same on the top and the bottom, is we're going to use long division to rewrite this rational function. So I'm going to take 6x and I'm going to divide it by x squared plus 1. Okay, so you're looking at what you'd multiply this by to get this, which would be 6x squared, a 6. So I get 6x squared plus 6. Then we subtract. These should always go away or cancel. 0 minus 6 is a minus 6. So I have a remainder of 6 over x squared plus 1. Now I'm going to rewrite my integral with that decomposed rational function. Okay, and then I have two things I can integrate. So 6 is going to become 6x. This one's a little bit sneaky, but it is tangent inverse or arctangent of x. Derivative of tangent inverse is 1 over x squared plus 1, so the antiderivative of that is arctangent or tangent inverse. Okay, and next two, I'm going to do some more u substitutions. So here my inside is going to be x cubed. So I'm going to let u equal that because its derivative is sort of there. We'll sneak a 3 in and undo it on the outside. My 3x squared dx becomes du, and e to the x cubed becomes e to the u du. Integral of e to the u is e to the u. And then we'll substitute back in our equation. 17 you might be able to do without a u substitution, but like I said before, it's a nice, easy strategy for us to use. Okay, so I'm going to sneak a 2 with a 1/2. Integral is still e to the u, and then we'll substitute. Okay, next we're going to be using some properties of definite integrals. So here we've got the integral from 1 to 5 of f of x is -1. The integral from 3 to 5 of f of x is 3, and the integral from 3 to 5 of g of x is 4. So with adding and subtracting, with the constant, I can pull that out. And I'm just going to split it up into two different integrals just to really illustrate what it is we're doing. Okay, so I'm going to have 2 times the integral from 3 to 5 of f, which is 3. And then the integral from 3 to 5 of g is 4. So we get 6 plus 4, which is 10. Okay, here we have the integral from 5 to 1 of f of x. Well, if I have the integral from 1 to 5, this is going to equal the opposite of the integral from 1 to 5. If we flip those in limits of integration, we get the same magnitude, just opposite sign. So since my 1 to 5 is a -1, -1 is 1. Here, be really careful about this one. So I'm going to integrate from 3 to 5 of g of x. And most common mistake I see is you just take that number and then add 7 to it. But we're integrating 7 from 3 to 5. Well, 7 would just be a horizontal line if we're looking at it graphically. So here, 3 to 5 of g of x is 4. This is going to be 7 times 2 because we're going from 3 to 5. If I was going from like 3 to 10, I'd multiply it by 7. But it's however far apart these are times this. Or do the antiderivative, which is 7x, and then subtract and do your whole definite integral thing. This ends up being 18. 1 to 3 of f of x. Well, I have the integral from 1 to 5, and I have the integral from 3 to 5. So what I can do is take the integral from 1 to 5 of f of x and subtract the integral from 3 to 5. What that's going to leave me with is the integral from 1 to 3, which is what I'm after here. Last one in this little section, we're going to use a u substitution. So I'm going to let u equal 1/2 x. This is a definite integral, so we're going to change those limits of integration. So half of 10 is 5, half of 6 is 3, and then my du is 1/2 dx. So I'm going to sneak a 1/2 in here, and then my 2. So my new limits of integration are 3 and 5, which is good news. And I've got f of u du. Well, integral from 3 to 5 of f is 3. So we're going to get 2 times 3, which is 6. Next, we're going to be doing some graphing. We're going to graph some known functions and use those to find the area under the curve, aka the definite integral. So first, we're going to have 2x plus 1. So that's just a line, y-intercept of 1. Okay, so 2x plus 1, slope of 2. You guys can grab a line. Okay, and we're integrating here from 1 to 3. Okay, well that's the area of a trapezoid. So we're going to have 1/2. The distance between the bases is going to be 2. And then my two legs, my two bases, sorry, not legs, are this distance and this distance. So it's the function when I plug in 1, which is 3. And it's the function when I plug in 3, which is going to be 7. Okay, absolute value we know is our v. If it's a plus 2, it's going to be moved to the left 2. Okay. So left 2, my v starts here. Okay, another way to think about this graph is if I took the line x plus 2 and then made it absolute value, so anything that would go below the x-axis gets bounced up. But we're integrating here from -3 to +1. So we've got two triangles here. This triangle is going to be 1/2, both the base and the height are 1, plus this area. So we've got 1/2. The base here is 1, 2, 3. The height is also 3. So I get 1/2 plus 9 halves, which would be 10 halves, or 5. Okay. The last one is a little bit tricky to recognize sometimes, but that is just a semicircle. We are integrating from -3 to 3. So we have 1/2 pi times 3 squared. 9 pi over 2. Okay, the function f is defined on the interval 0 to 6. Let g of x be the integral from 1 to x of f of t dt. What is the minimum value of g on the closed interval 0 to 6? So I'm going to check my endpoints and I'm going to check my critical points. So my endpoints are going to be 0 and 6. So g of 0 is going to be the integral from 1 to 0 of f of t dt. Well, that's going to be opposite the integral from 0 to 1 of f of t. And then I'm going to use my graph to figure out what that is. So going from 0 to 1 is going to be this little rectangle here, which is going to be 2. But it's going to be negative because of that flip there. My other endpoint is 6. that's going to be the integral from 1 to 6 of f of t dt. So we're integrating from 1, so we're adding this area here. I'm then going to turn around and subtract that equal area. So my integral is going to end up being that area. It's below the x-axis, so it is negative. And it's a negative 2 again, because we've got 1 by 2 there. The other point is where our critical point is equal to 0. Well, the critical point of g, derivative of this integral, is just f of x from that fundamental theorem before. We want this to equal 0 for a critical value. That occurs only at 3. So my last point I want to check is that critical point. G of 3 is going to be the integral from 1 to 3 of f of x, I guess f of t dt. So if I'm integrating starting at 1 going to 3, we've got the area of that trapezoid there, which is going to be 1/2. The height of the trapezoid is 2, and the two bases are 1 and 2. So we get 3. So if I wanted the maximum, that would be 3, but we want the minimum, which is -2. Okay, we've got the function, g of x is the integral from 1 to x of f of t dt. What is the value of g of 7 times g prime of 7? Okay, g of 7 is going to be the integral from 1 to 7 of f of t dt. So for this, we're literally just going to do the area under the curve from 1 to 7. Okay. So for this one, I'm literally just going to count boxes. So I've got 1, 2, 3, 4, 5, 6, 7, 8 whole boxes. And then I've got 1, 2, 3 half boxes, and then these two are going to cancel out. Okay, so if I get a common denominator here, that's 16 halves plus 3 halves is 19 halves. G prime of x is going to be the derivative of this, which is just f of x. So g prime of 7 is going to be f of 7. So we go to 7, which is at -1. So g of 7 times g prime of 7 is going to be 19 halves times a -1, or -19 halves. Okay, the function is continuous on the closed interval from 2 to 14. It has values shown in the table above. The function is increasing and concave down on the interval. What is the approximation of the integral from 2 to 14? And we're going to use a right Riemann sum and then a trapezoid sum, and then we're going to figure out if it's an over or underestimate. So first, a right Riemann sum is our rectangles. So the base of the rectangle is going to be the distance between those, which obviously is 3, but I'm just going to write it as 5 minus 2. The height, if it was a left Riemann sum, we'd evaluate here, but since it's a right Riemann sum, we evaluate on the right side, which is going to be 28. My next one is 10 minus 5 times the height evaluated at the right side, which is 34. And my last one is 14 minus 10 times our height at the right side. Now, we can leave it just like that, because that can be typed into a scientific calculator. What you don't want to do is just give the answer, so without showing the Riemann sum setup. Next, is it an underestimate or an overestimate? The piece we're going to work on is our function is increasing, and we are using a right Riemann sum. So I sketched myself a little picture. There's more area in those rectangles than actually under the curve. So a right Riemann sum is an overestimate on an increasing function. Okay, next we're going to do a trapezoid rule. Approximately. Okay, so the trapezoid, we've got 3 trapezoids. The height of the trapezoid is going to be the distance between the x values, so 5 minus 2. And then the 2 bases are the 2 y values, so 12 and 28. And then we'll repeat that for the others. 1/2, we've got 10 minus 5, and then 2 bases are 28 and 34. We've got 1/2, 14 minus 10 for my height, 34 and 36 for my bases. Okay, for this one, our graph is concave down. So if I'm doing a trapezoid rule, okay, we're leaving space unaccounted for. So a trapezoid rule, or trapezoid sum, either way, is an underestimate when the graph is concave down. Next, we have an integral function. So the graph of f consists of 3 line segments. Let g of x equal the integral from -1 to x of f of t dt. So first, what is g of 2? G of 2 is going to be the integral from -1 to 2 of f of t dt. So we're looking at our graph. Here's -1 to 2. Just here. So we've got this area and this area. Well, looking at it, this area and this area are going to cancel each other out because they're the same but opposite sign. So I'm just going to do this triangle right here, which gives me 1. Okay. If g is equal to this, then g prime of x is equal to f of x. So g prime of 2 is f of 2, which is just going to be the function value at 2, which is 0. And then lastly, the second derivative of g is going to be the first derivative of f. So we're looking at the slopes of this graph when x is 2, which has a slope of -2. Okay, then it says, is g of -4 positive or negative? So that's going to be the integral from -1 to -4 of f of t dt. Well, I'm going to rewrite this as the opposite of the integral from -4 to -1 of f of t. Okay, it's not asking me for the value, it just wants to know if it's positive or negative. So it's negative times the integral from -4 to -1 is going to be a negative value. So a negative times a negative is a positive. Okay. E, at what time during the interval has the smallest value, the largest value, and justify your answer. So our interval is going to be from -4 to 3, because it should say that better in the description. So I still want to check my endpoints and my critical points. Okay, endpoints are g of -4. So we're going to actually calculate it out this time. Okay, skipping ahead. Well, I've already established. So if I went from -1 to 4, we'd have here. So what we're looking at is the opposite of the integral from -4 to -1. Okay, so that's another trapezoid. And it's a negative, so I've already established it's going to be a positive. But so 1/2, the distance between the bases is 3. The 2 bases are 3 and 2. So this gives me a positive 15 divided by 2 is 7.5. G of my other endpoint is 3, is going to be the integral from -1 to 3 of f of t dt. Okay, so -1 to 3 is going to be all of this. Well, I've got the same area above and below, so this is just going to be 0. My critical points are when g prime of x, which equals f of x, is 0. That's going to occur here and here. So g of 0 is going to be the integral from -1 to 0, which is going to be the area of that little triangle, but negative. So we get a -1. Last critical point is g of 2, which we already found above was 1. All right, then we pick our winners. It says at what time? So smallest value is going to occur, we've got 0, 7.5, 1, and -1. Is -1 when t equals 0. Kind of the safe way to give both values, but the t equals 0 would be sufficient. Largest is going to be 7.5 when t equals -4. And the justification is the fact that we did our full extreme value theorem. All right, F. On what values is g increasing? That means when the derivative is positive. Well, what we're looking at here is the graph of g prime of x. So when this is physically above the x-axis, that's when the derivative of the graph we're not looking at, that says we're increasing. If it helps to do a number line, here my derivative is negative, here my derivative is positive, here my derivative is negative. So from 0 to 2, because g prime of x, which equals f of x, is above 0. Concavity is going to be the second derivative. So the second derivative is going to be the first derivative of what I'm looking at here. So when this graph is increasing, that means my second derivative of g is positive. When this graph is decreasing, that means my second derivative is negative. So we're looking for concave up, which is going to occur, like I said, when this is increasing from -1 all the way, or -4 all the way to 1. Okay, why? Because the second derivative, which equals the first derivative of that, is greater than 0. Or you could say that f prime is increasing. Okay, so point of inflection is going to be when the graph changes concavity, when the second derivative changes sign. So again, what we're looking at is the graph of the first derivative. So the second derivative is going to be these slopes. So when this graph goes from increasing to decreasing at x equals 1, that's going to be our point of inflection. So at x equals 1, g double prime of x, which equals f prime of x, changes signs. Okay, the slopes on f change signs because it goes from increasing to decreasing, which means our second derivative changes signs. So that is what you can expect for your Calc AB Unit 5 test.